Welcome, everybody, to the WaterCube Art of the Possible webinar. Today, we're going to be covering advanced hydraulic techniques utilizing 3D spatially collected data in rivers and reservoirs. So I wanted to introduce this complete series because it is the first in a series of events that we plan to bring to the community over the several months ahead. In April, we plan to share some case studies with regard to habitat studies and mapping springs within Florida on the Silver River, as well as modeling calibration studies in May, and finding hydrokinetic power and further identifying sediment accumulation for bathymetric studies in reservoirs in June. And then in July, following that, would be the flow monitoring and velocity indexing. So quick introductions. I'm Diana Krupa, the CEO of WaterCube. With us, we have John Sloat, who is the CTO of WaterCube, and our guest speaker, Art Schmidt, PhD and Research Assistant Professor at the University of Illinois. And he has been assisting us as our WaterCube scientist. So for those of you unfamiliar with what is WaterCube, we are a software, services, and data company. What we've brought to the market is a data processing engine for analyzing vast amounts of river and reservoir data very rapidly, but then also bringing that in a very seamless way into a visualization tool, Cubeit, which manages and manipulates the data, but it also can analyze it over time. The solution addresses many applications, whether you're looking at in-stream flow studies, sediment transport, hydropower and kinetic energy, hydrodynamic model calibration, even river restoration. And today, Art is going to be sharing across many of these topics the art of the possible. What are the possibilities of utilizing spatially collected and processed data like this, visualizing it and analyzing it in a way that applies to many of these various areas? So technology has come quite a long way, and it certainly has enabled us to do things differently with the data collection efforts and methodology. Going back in the 90s when there was a single frequency ADCP, it certainly took much longer to collect some of the data that you require for discharge or other types of measurements. But as you went into multi-platform sensors and a fully integrated system, it became much easier to utilize this technology with integrated GPS and telemetry. Today, we can take multiple instruments and hit the water together in parallel to collect multiple lines of data and rapidly process that together to give you a full digital elevation model with inlaid velocities. Now, with all this technology comes opportunity, but it also provides still a workflow challenge. And so what we are trying to do at WaterCube is make this a much more seamless experience for the end users, whether they're modelers, hydrologists, or scientists. We are trying to take complicated technology and seamlessly put it out on the water to help you collect the data, QA, and process that information, and including even LiDAR, if you may have it, in a way that's giving you more immediate results. So WaterCube is truly an integrated visual solution for managing your river. We assist in the advanced data collection, or we take the data you provide us directly. We do a quick engine in terms of processing and delivering those results. And then the visualization is on the back end. So I'm going to talk for a minute about some of the rivers and reservoirs that we've cubed, but I also wanted to take the opportunity to thank everybody on the line today that's in attendance. And I waited a few minutes to do that because we didn't have quite everyone on. But I do want to recognize that we have quite a few of the water management districts on the line, some larger consulting organizations, a few of the hydropower companies, as well as USGS, who are here in attendance, and we thank you for that. When I talk about some of the things that we've done, we took a lot of time to make sure that the data we were collecting and the technology that we were producing could be, fruitful in terms of defensible as well with the technology applied in a new methodology, but also providing results that our clients needed. So I'm going to take you through a very quick view of some of the rivers that we have analyzed thus far and validated with our technology. So we had the great pleasure of working with the St. John's Water Management District in Florida on the Silver River and their springs. In Florida, we've also mapped a portion of the Rainbow River. We've utilized other technologies such as the IVER AUV by Ocean Server for the Tampa Bay Ship Channel. We've looked at the Spring Garden Run in Florida. Moving out to the Midwest, we had a great opportunity on the Snake River looking at CJ Strike Dam in Idaho. And this is going to be one of the case studies that we dive into more deeply on this particular webinar. On the Snake River also, Swan Falls. As we go out to the West Coast in California, we've mapped the Sacramento River, not the entire river, but certainly many kilometers of that. And then coming back in, showing that there are additional studies we can do utilizing different technology, dual frequency echo sounders, to look at reservoirs and sediment accumulation. As we go across the pond into the United Kingdom, we've mapped the River Severn, as well in Scotland as River Nain, and the Stordselva River in Norway. In Australia, we've worked with a certain organization or research organization looking at many of the rivers flowing into the Great Barrier Reef. And in South Africa, the Vilhay River, and this is a particular site that's being studied in further research for a study on methodologies of data collection, spatial versus transect, and looking at how they benefit the pros and cons of one another. And for the application at hand, which one you may want to apply. So as you can see, we've kind of gone around the world a bit to develop case studies and further enhance our technology to make sure that it's meeting the needs of our clients over different rivers as well as different applications. So how is it all done? We're going to take the example that we briefly shared on the Snake River in the CJ Strike Dam. So just to go through a quick step-by-step process, we will come in working with you to plan your survey. And these are true ADCP track lines on the right that have been collected. In this case, there were 4 separate track lines, or 4 separate ADCPs, excuse me, utilized to collect all of this data. In the top right, we have the spillway. On the bottom, we have all of the turbines. And in this area, this is where there was an instrument placed to monitor flow. Data collection, as I mentioned, was done with 4 ADCPs in parallel and staggered, along with a remote boat as well that was put on the water. And just to mention, in terms of the study, this was something where they were alternating different turbines, getting to steady state, and then having a measurement methodology that would go with the flow. So there were techniques utilized to go with the in-stream flow, as well as cross-sectional hatch patterns that were made to look at deeper resolution and identify specific transects within areas along that river. So by combining multiple ADCPs, we get the bathymetry. We can bring that together with existing LiDAR and create a complete topography. By doing that, through our processing, we then layer in those velocities. And the velocity that I might want to point out here is truly 3D, and it's a volume of all of the velocity throughout that river. And we do say that it is a cube of your river, and that, therefore our name WaterCube. The velocity is laid into the complete elevation model, so the grids are aligned, and then you have a complete digital elevation model with your velocities and depths throughout. Once you're done with that, you can visualize and analyze it within the Cubeit software. So Cubeit was created to bring these data files seamlessly in and give you the ability to analyze, but also manage your data and compare over time. So I'm going to give you a quick view and visual of the CJ Strike Dam on the Snake River. And I'm going to ask Art to also chime in and talk about how this would apply for many of the applications.
Okay, so we're running here and we are looking at this in the Cubeit software. And what you're seeing is we have both the digital elevation model merged with bathymetry from the ADCPs and then the downstream velocity. I should mention we have the full 3D velocity field, so you can do a downstream velocity, a cross-stream, XYZ components of velocity. There's the opportunity to look at things such as helical flows, circulation patterns, and so forth. You'll notice here we're zoomed out a little bit further. You can see the spillway on the left, the powerhouse on the right, and sort of in the center of the screen you'll see there's a bridge, which is where the existing index velocity station was, and a scour hole on the right-hand bank. It'll be your left looking at it upstream of that. We're now doing slices perpendicular to the flow, and so just through the 3D field coming up with slices that we can look through and so visualize in more detail where you want what the velocities are doing. And as you go through the slices, I believe we'll run through this another time, but you'll notice near that scour hole some very high velocities. So you're starting to see the interplay of the water, the hydraulics, and the stream bed. A little bit further zoomed in here, some of the scour things show up a little bit better. We've got a little bit change in the ratio here. Again, you'll see some of the high velocities where we've got these scour holes and so forth. And we'll talk more about this a little later. We can do our slices in any direction. From an arbitrary plane, you can specify the coordinates, X planes, Y planes, Z planes, which are horizontal planes. And so I believe what we're going to have here is a series of horizontal slices now, starting from below the stream bed and moving up a little bit as we go. So waiting for the video here, but you'll see this ability to take the slices looking through in the horizontal direction. So what's happening at different distances below the stream bed? I guess we're back to the slices perpendicular to the flow here. But again, a lot of the strength of this is now, instead of just looking at the surface or a few select spots, I'm starting to be able to look at through my entire water column. I jumped the gun. Now we're going to get the horizontal slices. So we started, and you can see with the deeper spots we have velocities, and then as we move up through, you can see what is the velocity field, again, at different levels through the water column. Now we're looking at an aspect of the Cubeit software lets us look at multiple measurements at once. So I think Diana mentioned on the Snake River at CJ Strike there were 4 different data collections. I'll go into more of this with a live demonstration, but different seasons, different flow rates, different water elevations, and now we can look at all the slices. Each column here is a different data collection date. So we can start to look at, from whatever parameters we want, what was happening over time in the river and do these side-by-side comparisons. And I will talk a little bit more about this in the context of flow measurement and identification of flow measurement and velocity indexing sites.
All right, thank you, Art. And we will transition to that in 1 second. What I wanted to do now is just give you a quick overview, because we took you through a full cube, which was the complete digital elevation model with the velocities inlaid. But there are other things that we definitely have in terms of processing services so that you can quickly hit the water and get some of the data that you need. To the left, there's the ability to just go out and do subcubes and take a portion of the river. and maybe even do, like I mentioned earlier, the crosshatch pattern with greater accuracy in terms of some of the data being collected, because we're doing quite a bit more data collection, and then looking at it in more detail. Another way of taking information in terms of transects for specific habitat studies or other modeling efforts is also to do a single line projection, where you'll take the ADCP across and project it into one transect that can be utilized for all of your studies. And then lastly, bathymetric. So I mentioned briefly that we've been doing and utilizing other technologies, whether it's an echo sounder or a dual frequency, but being able to look at bathymetry and sediment accumulation in reservoirs, lakes, and so forth. All of this then is seamlessly put into Cubeit. Now, one thing I wanted to mention here is that Cubeit is our visualization tool to help you manipulate the data and look and analyze further, but all of the processing output can go into different formats. So it is not necessary to have Cubeit only to visualize. You can certainly take this into other programs such as ArcGIS and so forth. So now I'm going to hand this over to Art for him to go into deeper detail on what you can do.
All right. And Diana, is my screen showing?
It is.
Okay, and I've backed up just a little bit. The first part of what I talk about, we didn't hit this in great detail, but you'll notice where the circle on the right here says instrument placing, there are a bunch of measurements done perpendicular to the flow. I will call these transects, but it's the traditional measurement we've often done. There's also all of these measurements, and I'm going to call these go with the flow, but Diana showed the picture of the boats moving downstream. And that's going to become important as I talk a little bit. So I'm going to give a little bit I'm going to compare what we've always done with some of the new things we can do, and then Diana likes to call this the art of the possible. I'm sure the play on my name is deliberate. But I want to talk about some of the different things we can do. And just a little bit of background. I'm sure there's several out there that know me, but my background goes way back to working for the U.S. Geological Survey for about a dozen years. And just a variety of different things, but there is that background in data collection and analysis. I then have some time in consulting before coming to the university where I'm at now. My relationship with John Sloat goes back better than 20 years, and we've done a lot of work, different measurements in different areas, and then as time went on, some short courses. And about a year and a half ago, as John and I were doing a short course related to velocity indexing, he started showing me some of the things on Snake River that had been done. That study, a lot of that had to do with velocity indexing. But as John started to show me this software and the things they could do and how they were collecting data, I got very excited about it. And just the possibility of seeing and understanding a lot of things in our rivers that we hadn't seen before, or that we had to make a lot of assumptions and interpolations. And so that's some of where this comes from. It was very exciting to me to think of some of what we could do. And so as I talked with John, they provided me with some of the software, and I started looking at what could be done. So some of the things I'm going to show are still research. They're still being refined, that what's the best way to do it? How does the data need to be collected? But I want to put out there what are some of the things we can now do. And I'm sorry, I got behind here. So back to some of our traditional analysis. This comes from the textbooks. Most of you are familiar with this. We want to measure the discharge in a stream, and so we set up a cross-section as perpendicular to the flow as we can. And in the old days, we would do a bunch of verticals. We would break the stream into 25, 30 different panels, and we would measure a depth, We'd measure where we're at, and we'd measure the velocity at 1 or 2 or maybe, if we're ambitious, 3 points in each vertical. And use that to come up with an area of the flow and a mean velocity and a discharge. As the acoustic Doppler profilers came out, we now have this instrument that, instead of a few points in the vertical, can measure the entire vertical, and it can measure the boat movement. So this got replaced largely with moving boat measurements, where we would still move perpendicular to the flow and do multiple passes or transects, but we'd no longer, in general, sit at one point for a long time. There have been studies that looked at what's the difference between doing moving boat transects and sitting and doing stationary or panel by panel or section by section, whatever you call measurements. And you have a trade-off that if I sit at one point for a long time, I get more averaging of the turbulence. I get a better picture of the vertical velocity at that point, the vertical distribution of velocity, but I have to interpolate what's happening from point to point. If I do a moving boat, I have noisier picture of the vertical distribution of velocities, but I fill in those gaps laterally. And so we have this trade-off between, are we averaging in space or in time? And it turns out for discharge measurements that either way does a fairly good approach. And so what's been done then, even when we're mapping rivers, and this is from a USGS report, it was on a model study on the Ohio River, and this is not to pick on the USGS. We have to keep in mind that the purpose of this data collection was more than just what's happening for the entire 12 miles. But I wanted to illustrate that in a 12-mile reach of river, there's 15 lines that the data were collected. ADCPs were used to do the transect, and then there's a lot of space. This means we have about a 3/4 kilometer spacing of transects. So we have much denser data across the river than we have longitudinally. And so I've been doing some research, and Diana mentioned the South Africa Division of Water Affairs has been very generous. And as part of a data collection they're doing on the Vilhay River, they have done both the stationary measurements, the transect type measurements, and the go with the flow measurements concurrently, so we can start to look at what are the trade-offs that if I want to ask different questions, such as what's a velocity profile at a point, what's a distribution of shear stresses in the channel, what's the flow rate in the channel, what kind of trade-offs do we have between different measurement approaches and then measurement densities. There's also trade-offs with the time. Although we'd like to treat the river as steady, in reality, rivers didn't go to school and know they're supposed to be steady. So there's trade-offs between how long it takes to do it and the kind of uncertainties we have. So I have a PhD student that's working on these, as well as some of the other things we'll talk about today. In general, what we do now, though, for sparse data is we do a numerical model. And numerical models are great. They can help us deal with things such as the unsteadiness, such as where we don't have data. But we need data to calibrate these, and then we can interpret from the models what some of our spatial and temporal variability. So this is just showing some work that was done here at the university by one of my colleagues in a model of the Chicago River, and giving an idea of the kind of grid. And once again, the data to develop this is sparser than what we have. And I'll talk more about this a little bit later. This is back from the USGS report. So you see one of the transect lines, and in the red you see the red vectors are from the ADCP. We've got a good picture of the velocity field. And you'll notice the density. We have very dense measurements of the velocity along this one line. The bluish tinted vectors are based on the model grid. So you'll immediately notice laterally our model grid is not nearly as dense as our ADCP data. However, longitudinally, instead of one line, we have a lot more data. And so this issue of how do we interpolate between transect lines has been around for a while. Different people have looked at it in bathymetric studies, modeling studies. But one of the beauties of what WaterCube has done is you can now look at your data for the entire reach. Again, at the expense of it won't be as sparse longitudinally, but you'll have sparser, denser data in the longitudinal direction. So I'm going to jump to the CJ Strike, the Snake River, and flow monitoring, and particularly velocity indexing. And for those who aren't familiar with it, a lot of times we'll have streams where a traditional stage discharge measurement doesn't work. So we put in an instrument, usually a hydroacoustic instrument, that's measuring the velocity in some small subsection of the flow. In the middle of the channel here, you'll notice a blue box that's trying to illustrate we might have a side-looking instrument set up to measure the velocity in this one small subsection. And the idea behind velocity indexing is that there's a well-defined, unique relation between the velocity in this subarea and the mean velocity in the cross-section. And in other words, the velocity distribution in this channel will be fairly constant over time and over all flow conditions. And if that holds by measuring the velocity in this small area, we can get a good estimate of the discharge in the entire cross-section. The problem is rivers don't always do this. So we're going to come back to CJ Strike here. Again, we've got the spillway on the left, and the powerhouse has 3 turbines. It's on the right. And in the LiDAR data, you can notice the road coming down from by the powerhouse, and then there's a bridge over the river here, then the road comes back up the hill. And there was a index velocity meter near this bridge, and for a long time it worked very well, but if they were running one turbine, it was always the same turbine. 2 turbines, it was the same. Well, that operation rule does not work well for longevity of the turbines. So when Idaho Power switched, they would run different turbines instead of always the same one. The velocity index rating went got very bad. And what you had happen is, depending which turbine was running, your velocity distribution of the channel would change. So they collected a lot of data to look what is happening and how do we move or redo this instrument to get a better idea of what's going on. So what this graph here shows is 4 different flow conditions, and there were different flow rates, different seasons. Some of these were August, some were February, different turbines being run. And at the bottom, I'm showing for the 4 flow conditions a good site for velocity index. The contours are the dimensionless velocity. So what you should have is the distribution of velocity should be the same no matter what flow condition. And you can see at this one site, we have the highest velocity always about the same time. It's fairly large, so if there's a little bit of shift, it doesn't change it. And you've got a strong signal-to-noise ratio. You've got very high velocities relative to low other places. On the other hand, here's another site, and you'll notice how the maximum velocity changes from the center of the river on the left to way over near the right-hand bank, or the left of your graph in this second graph. And then sort of spread out, you've got 2 maxima over in this far right-hand. And so this is not a good site for velocity indexing. You can very visually see how the velocity distribution is changing across the channel, so wherever we measure, it's going to have a different ratio to the mean depending on flow conditions. So that's just one illustration of how this can help, as the engineer, the hydrologist, you can get a better understanding of what is happening in my river and then couple that with your expertise to do your job better. A lot of things, a lot going on these days with habitat, endangered species, invasive species, looking at the suitability of habitat for different species. And so I'm going to talk from the concept of fish species, but there could be a lot of different things this couples to. And so there's different factors that will impact habitat suitability for different species. You have to have the studies of what my species can take. But if you look at these parameters, all of these things are things that can be calculated from the kind of data we get from an ADCP. And then if we've done go with the flow measurements, we have the opportunity to calculate them for an entire reach. And so taking some studies done in the West, Brown and Pasternak used Shear Stress and these habitat suitability indices based on depth and velocity, and they developed what they called a generalized habitat suitability index. And there's some other things, but again, all hydraulic factors being considered here. And so, again, just repeating what I said, the data we have just from ADCP, along with maybe a little bit of sediment sampling, can calculate all of these things. So what do these indices look like? This is one the Fish and Wildlife Service developed for Chinook salmon spawning. And so a value of 1 is the highest habitat suitability, 0 is the worst, and so you have this 0 to 1 index showing, in this case, your ideal depth for spawning is a little bit over 1 foot, and your ideal velocity is about 1 to 1.5 feet per second. And so if you're doing habitat modeling, for example, FabSim, you would calculate your depths and velocities and apply this. We can do the same thing with real data. So on the right-hand slide, this is CJ Strike again. And what I've shown is I've got the along stream velocities, but then I have also calculated a habitat suitability index. So I'm showing the velocities as the contour lines, and then the bands are showing the habitat suitability index. So we have areas where the habitat is very suitable for Chinook spawning, but other areas, either based on depth velocity, it is not suitable. As we talked with some fisheries people about this, the question came up several times is, what we're really interested is we want some specific distance from the bed. I showed you earlier the ability to look at horizontal slices. They said, can we see the velocities a fixed distance from the bed? And the answer is yes. We define that surface based on the bathymetric measurements and then shift them, and then we can take and from the data come up with what is the velocity, that fixed distance from the bed. So I'm showing on the left here data from the River Severn in England, and showing in this case it's a dimensionless velocity 1 meter above the bed, as well as the along stream velocities. So I am going to jump here and back to the CJ Strike data. And so what I am showing right now is I've got the topography here. I have contour lines showing up are the depth of the channel here. And then in the tint, it's the light blue tint. This is a different flow condition than before, but it's a habitat suitability index. And one of the things to notice is this is one of the higher flow conditions. The other one was this was in February. The other one was in August and a lower flow. And my habitat suitability has moved, so I can look under different flow conditions. I've also set up the slices, the horizontal slices like we did before. So I can look through here, and I'm going to slow this down so it shows up online. But I'm going to look at just horizontal slices from the bottom up, and this is the along stream velocity. So if you're interested in a certain distance below the water surface, we have the data that we want here. I can also change this. I can look at my slices in the X-planes. And again, slow down the animation. And so I can look at what the velocity distribution is along the channel. And then I have also set up 1 meter above the stream bed. And so here is our along stream velocities 1 meter above the stream bed. And it could be 1 meter, half meter, whatever is relevant for the species you're looking at. And again, I could overlay this with the slices here. So now you're seeing this 1 meter above the stream bed. We've also, everything we've talked about is ADCP data, but it doesn't have to be. So this is CJ Strike, and fair disclosure here, I'm showing 50 water quality measurement points. Idaho Power did not collect water quality, so I picked 50 points at random, and I put in as if we had thrown in a data sonde or one of the sensors and come up with a profile of our water quality. So this is fabricated data for the water quality, but what I wanted to point out is you have your coordinates. You have an X, Y coordinate where you put your probe in, you have a depth, and you have the values you've read. And Cubeit does not care where the data comes from. If I put in the data, I can put it on my field. So using the data from these 50 points, this would be a map then of the specific conductance. Again, fabricated data, but the specific conductance. So now we're able to start to look at, had it been real data, are we seeing any patterns from what we see in the flows, the velocities, and what we see in water quality parameters. So the art of the possible, but we can start to merge different sensors, different instruments, and come up with more understanding. Diana mentioned next month's webinar is going to be on some of the work in Florida, and the Water Management District had done a dye study, and we've done a little looking with plotting stream traces where we can numerically put in an injection and then use the measured velocities to see how that moves and compare that with the actual dye data that's been collected. So just a trailer for next month. Sediment and deposition caught my attention a lot. There's a lot of work in river restoration and engineering looking at sediment scour and deposition, where it will occur, what impacts will have, channel geomorphology, and so forth. And realize we have the data to look at this like never before. So I teach this all the time in my undergraduate courses. When we're designing a channel or looking at sediment transport, shear stress is our big measure. This is what moves the sediment from the stream bed. And so when we're doing this, what we always do, and I've got the equations here, but we calculate a reach-wise average shear stress based on the geometry of the channel and the specific weight of the water, and then the slope of the flow of the water. And so this shear we calculate is the mean and the cross-section. It's an average shear, but our river did not go to the University of Illinois. It does not realize it's supposed to obey this equation, and so you actually have your shear stresses varying all over your cross-section and from cross-section to cross-section. So if I'm doing engineering design, what we do is we'll typically calculate a maximum shear where I've changed, instead of the hydraulic radius, a calculated hydraulic parameter. We use the maximum depth of the flow, and we calculate then the maximum shear based on a maximum depth. And then we couple this with a factor of safety because the shear is not uniform or constant around the cross-section. But if we go to a more fluid mechanics perspective, the shear at any point, this messy equation here basically says at any point the shear on the bed is proportional to the velocity gradient, how fast the velocity is changing as I move away from the bed. So if now I have these data giving me velocity profiles at points throughout my reach or my cross-section, I can calculate this velocity gradient and hence calculate the shear stress throughout my reach. So we took the data from CJ Strike, and I've shown it here, but let me come and go back to a live demonstration. And so again, here we have our CJ strike reach. And what I've done, once again, it was fabricated data, but I took a couple hundred points randomly picked throughout the reach and said if we had done bed set material sampling, if we had a grain size, and I put that in at XY coordinates, and then let the Cubeit software carry those sediment distributions through the whole channel. I then followed the equations we looked at before, and I calculated what is the shear stress, and then here I'm showing this parameter shield stress. And what shield stress does is couple information about the size and density of the particles to determine what is the force it will take to move a particle, and then compare that to the shear from the flow. And so the shield stress is a dimensional measure of basically how likely the particles are to move. And so a low shield stress means we're not going to have scour there. A high shield stress means it's very likely to scour. So what I have here is I've got the ground elevation contours. I also have a map of the sediment grain size, again from those, they're dummy samples, but the distributed where we had those. And then I'm showing the shield stress and showing we have these spots where we're likely to have scour occur. And so once again, showing how we can take these data and go from a reach average or cross-section average value to start to look at what's happening throughout our reach. Again, this depends on the density of the data you've collected, how it was collected, but the potential is there to look at these things and do the calculations with the data that we have now. And then I want to talk just a little bit about model calibration. And I've shown this figure before, and again, I guess this is a different cross-section line, the same report, but once again, very dense data laterally, very sparse longitudinally versus our model values, which we have everywhere. And in general, what we do in our modeling is we'll take a figure like this and say, look, you can see we've done a pretty good job. My directions are right. We've got the high magnitudes here, match the model. We've got the low magnitude and the reverse flows. So in general, we've done a really good calibration here. And I would agree with that, and that's taking advantage of the modeler's expertise and their judgment. They've done this. And yet, especially as we get to more complex models, we're often missing, do I have any sort of numeric thing, any statistics, things that will better tell me what's happening? And so we're looking at, instead of just the lines and things like this, can we look at an entire reach and come up with some statistics, some measures, some figures that will help the modelers better calibrate and validate and understand their models, or where they need to refine things or gather more data. So this is some work. The St. Johns River Water Management District has developed a model for the Silver River. So in the small grid I'm showing here is the Cubeit grid. So that is the grid used in Cubeit. All the ADCP data are then interpolated onto this grid and output. The larger grid is the model grid from the St. Johns River model. And what we've done, because the software can take and interpolate at any point, just like we can shift the surface up from the bed, we now can take in Cubeit and at the centroid of each model grid, taken from the nearby ADCP data, come up with an entire field of the velocity vectors at each point on the model grid, now allowing a one-to-one comparison of what is the modeled output compared to what the ADCP data are giving. And so in future webinars, we'll talk more about this, but it's just one of the other possible things. I know I've looked at things like stream power and such, but I think I should quit now and leave a little bit of time for some questions.
Great, thank you, Art. At this point, we're going to open up for questions. In your webinar window, you should see an area that looks like this for questions. If you want to type them in, I'll field those, and we'll ask everybody that's on here that can answer. And John Sloat, would you, he's also here, so I'd love for you to answer one of the first ones that's coming in, actually, that I already see. John, are you with us?
Yes, I am.
Okay. The question was, within some of the views previously seen, we were talking about bathymetry as well as some other surveys. So is this representative of a hydrographic survey?
Okay, so yeah, to that point, what we do is that we process the bathymetric data that you provide us, and so and we're in terms of classifying as a true hydrographic survey. We process the data based on what is provided to us. In many cases, it's data collected with an ADCP or multiple ADCPs using a 5-beam or 4 or 5-beam solution. In some cases, it's using single beam or multi-beam sonars or echo sounders. And again, all of these data are collected to different standards. And so we will take that data, process it, combine it, if required, with different technologies, and then produce a bathymetric survey. So I don't know if that addresses the question specifically, but yeah, in terms of ISO or type of hydrographic standards, if you've collected data to those standards, that's what the data will be. If you've collected the data to your own local standards, that's the data that will be produced.
Okay, thank you. A question around vegetation. So I will say this, there were multiple questions around submerged and emergent vegetation that were asked. And one of the case studies that we will be doing next is the Silver River and Silver Springs, where they have submerged hydrilla. But the question is really around understanding how the technology works in this heavily vegetated stream. And in Florida, of course, it's a big concern. So not only with the vegetation, but soft bottom sediments. So do you want to maybe comment, both Art and John, on that?
I'll let you take
John,
that,
you
Art.
want to go first? What's that?
You can go first, Art.
Okay, well, it's almost like John said before, what this gives you is good as the data you've collected. So if I'm using a high frequency instrument that doesn't have much ability to penetrate, I'll have no data very deep into the vegetation, and so I can't get anything. On the other hand, if I'm using a lower frequency instrument or a multi-beam instrument, I have more ability to penetrate through vegetation, through soft sediments, and so it comes down to taking and knowing what the limits of your instruments are, using the right instruments, knowing what's going on in your river, and then designing a study that can answer the questions that you're looking at.
Yeah, and just one comment to add to that. Yeah, in terms of the data screening, for example, again, for example, back to the Silver River, quite frequently when the ADCPs are tracking, they do track quite well, actually, over the vegetation, the submerged vegetation, because it's so dense. And so really, we're not providing, in that case, it's not the true bathymetry of the river reach, but actually it's more or less the flow depth along that river reach. And again, we'll take that data. We do screen the ADCP data or the multi-beam or even the LiDAR data. We screen these data for outliers and quality. But again, a lot of it is highly dependent. It's critically dependent, I would say, in terms of the quality of the data collection itself.
And I think that lends itself to the next question around ADCPs and the use of that for extrapolating in some of the zones that may not be measured, whether it's near the bank or on the bed itself. And how do we analyze for that? And basically, how do we extrapolate the data? John?
Oh, okay. I wasn't sure if that was for Art or myself. Yeah. So we're using the similar extrapolation techniques that are used in the ADCP flow equations now. Some of you are more familiar with them than others, but basically the profile extrapolations for the top and the bottom are, have been clearly, pretty clearly documented in a lot of publications. We're using those, and along the edge extrapolations, we do the same.
And again, with LiDAR tying that in. I don't know if you want to mention that from a bathymetric standpoint for tying it all together.
Yeah, well, LiDAR, we use LiDAR, again, it's most useful when you're trying to understand floodplains. It's obviously a lot of data, but when we stitch all of that data together, the LiDAR data also is quite helpful for determining a particular boundary interface between where the water is and where the land surface is for that flow.
And I would just comment, I mentioned art of the possible, and even with the sediment and shear, the best data for calculating shear is right at the stream bed. However, that's where there's limitations with the ADCPs. And if you use everything right to the stream bed because you've used the instrument's extrapolation, what you're going to get is what assumptions you made in doing that extrapolation. So some of the research I'm doing is looking at then if we use data a little higher up in the water column, then we're not subject to those extrapolations, but what kind of uncertainties do we get, and looking at trying different resampling techniques. And we'll talk more later webinars, but how's the best way to estimate these shear stresses given the limitations of the instruments?
Great. And there's actually a technical question, John, around the ADCPs that we've been looking into ourselves. In fact, for using ADCPs and the slant beams for bathymetry, do you worry about ray bending in the stratified reservoirs affecting any of the accuracy of the depth? And so therefore, there's probably multiple instruments you can apply to something like this. But John, do you want to address that?
So the question specifically, Diana, is the utility, if I could rephrase it, the utility of using an ADCP in reservoirs for bathymetry? Yep.
For accurate, yeah.
So,
exactly right.
Just to clarify for everybody, as the transducers or any transducer emits a pulse, as we go through density layers, it's going to shift basically, and as it shifts, actually the depth that it provides is going to be, not the true depth. And so you correct that. Primarily, it's corrected in today's terminology using sound speed profiles. And sound speed profiles can be collected with instruments like the Wi-Fi Castaway. There's numerous other direct reading sound velocity meters, but sound velocity profiles are taken, and then these corrections can be made. In particular to the ADCP, the question is very correct. When you have a slant angle, it's going to actually shift a lot more and could produce errors, especially if you have a lot of pitch and roll. And so, if on my choice, you're going to do a trade-off between, like, for a vertical beam transducer that won't be as susceptible to that, but you're giving up some spatial coverage in terms of being able to get a swath, if you will, from the ADCP. But again, this is back to the data collection, the quality control. These instruments are highly sophisticated. They do produce numbers, whether they are altogether correct or not, and it's really up to the data operator to maintain that and to make sure or maintain the integrity of that.
Okay. I did have another question from Spain. Hello and welcome. Just really understanding a little bit more about how to get the software and basically how do we engage with folks out of the country and how do we get people trained on that. So I just wanted to address that. WaterCube can provide guidance on the survey itself for data collection, or in fact, utilize existing river teams that we have in the local regions internationally, and potentially even do it ourselves. So there are multiple ways of addressing that. We have much of the technology that we can put on the water in terms of collecting the data, so that is something that can be a turnkey offering by WaterCube. However, we'd love to teach you how to fish as well. So we typically will train you on how to collect that on an ongoing basis, and then we would take those data files, process them, and deliver them back to you in Cubeit, fully ready to go. You just fire up Cubeit and you have your visuals, your images, and your full digital elevation model already there with layout files that have already been basically put into the software. So it's a pretty turnkey solution in terms of being able to take your data or collect it for you, process it, and then you have it ready to go, and scientists can analyze away. Okay, we have about 2 more minutes or so till we're going to end the session, but there were a couple more technical questions that came in, and John, I think you can address these along with Art, but it asks about interpolation schemes when we're collecting and doing spatial averaging. What type of interpolation scheme is used?
I don't know how much, John, stop me if I get into anything too proprietary here.
I will.
I'm not going to go into all the details of it, but essentially we're weighting based on the distance. And so we identify points that are within a search radius of the point we're interested in. There is a filtering then. There's a vertical interpolation then because all the points may be a little bit different in the vertical, so we have to take those into the layers that match what's being done in Cubeit. Again, quality assurance checks, and then an interpolation that's being done with weighting based on the distance from your point. But I don't know if I can say too much more than that.
Yep. And just a kind of a point of reality here. Let's not kid ourselves. You know, the instruments that we're dealing with in today's world are capable of collecting large amounts of data very quickly and very spatially, and really what we seek to do is to take advantage of that. And so we do take seriously and we're very careful about how we apply these interpolations and so not. And you're right, Art, I think you took it as far as you should. But nothing can replace the amount of data collected correctly. And so basically the more data you can collect in the shortest period of time are really going to produce, you're going to have more confident results, more reliable results overall. And that's something that we do frequently. Back to the question in Spain, you know, one of our recommendations is to let us actually go out with you the first time and walk through the process. There might be things that we don't see in the field, or that we see in the field that we can't relay to you. And so we are very conscientious about the data collection. We consider it the most critical part of what it is that we're doing. It should be done correctly. We should collect the correct amount of spatial data before we start the first data screening or data interpolation and, you know, presenting it on a map.
Great. Well, with that, I think I'm going to have to end this webinar. There are just a few more questions that were coming in that we can address via email and send out some of the answers to that. I want to thank everybody for attending. We greatly appreciate it. And please don't hesitate to contact WaterCube directly on our WaterCube Data page, which is our general landing page. There's also an inquiry tab for you to send us emails. And the one thing I wanted to also mention is that we do have a kayak giveaway. We already had a winner in 2015, Thomas Gast. He is out on the water as we speak, utilizing this blow-up kayak, which is fully capable of taking on your instrumentation and hitting the water pretty quickly to gather the data. But I'd like to invite you guys to come out and at least put your name in the hat for this year's drawing of 2016. And also, if you have not already done so, on our resources page, download the Art of the Possible white paper for attending. And we just thank you all again. Have a good day.
Yep, thank you.
Bye-bye.